For today, there are three major concepts you have to have nailed. I put them on the whiteboard over here. So the phrase statistically significant is a phrase that we're going to use from now till June. Okay? The 30 to 40% of this class, which is mostly all second semester, is on statistical inference. Okay? And every one of those problems usually ask you at the very end, is it statistically significant or not? Okay? Because if you're doing these calculations, you have to make a conclusion. Your conclusion is based upon if your results are statistically significant or not. Okay? A couple weeks ago, Max and Tiffany came in my room. They needed help or wanted something about a t-score, right? Yeah. And the t-score was like -4, right? Now, all a t-score is it's a z. Okay, so if you have a z-score of a -4, what's the probability of that happening on a normal distribution? So 4 standard deviations from the mean is how much area in the tail? The table only goes to like what, -3? Yeah. So a -4 is off the chart, right? So how much area in the tail is a z-score of -4? Minuscule, right? 0? All a t-score is it's a z-score, but you don't know the standard deviation of the population. That's it. So that t-score of -4, what was the p-value? You remember what the p-value was? 0.000000. The conclusion, I don't even remember what that thing was about. The conclusion is this, that is very statistically significant. Meaning that the probability of those two things happening, listen carefully, by chance is about 0. Okay? And I don't even remember the context of the problem. But if you get a p-value of less than 0 or less than 1%, you would call that statistically significant. Even 3% statistically significant. 5%. So what that p-value tells you is it's the probability of that thing occurring by chance. Okay? So, statistically significant, I'm going to give you another analogy to illustrate that in just a minute. The other thing is blocking, which is what this second slide is devoted to. This is really pretty much a concept you have to understand. I'm going to ask you to respond to part C of the Frappy in a minute. Blocking is a huge, huge concept, probably the most important one in this chapter. And then something called matched pair. Okay, so those three things there is going to kind of finish off this experiment. And then, so you're going to finish the Frappy today, you're going to do a couple bookwork problems, we're going to watch a video just like we did here. So after I talk to you about statistically significant, we're going to read out of the textbook that. Okay, and I'll have Max not here to read, so we'll have someone else read. And then we'll watch a video. Then you guys will try number 77. And then you'll do part D on the free response question. Okay? The last thing, matched pairs, we're going to do an activity where you're going to take your heart rate in 2 different fashions, but please wait for directions on that. So we'll do an activity to illustrate what a matched pairs design is. Okay? And then I will give you all the grading rubric for the free response question, and you're just going to grade each other's work. You're going to give each other a score either from 0 to 4. Okay? Then I will show you an exemplar free response to that, and so you can kind of gauge to see if you were graded correctly or accurately. Okay? And then there is a nice workbook summary, which remember I asked you to get your workbooks last time. So on page 63 through 66, number 1 through 10 puts all of these concepts in a blender. It's a real quick check if you guys know how to put all this together. Okay? The first thing I had up on my agenda, though, is any blanks. I added that in because I forgot about this paper. Now, those of you that tried it, I don't want to hear from those of you that didn't try it, but those of you that tried it, is there anything you don't know what to fill in yet? Yeah.
The statistical analysis techniques appropriate for this study. It's like the second to last one.
what statistical analysis techniques are appropriate for the study. Okay? Remember Max last time during the middle of the free response, he says, do we have to be specific? Can we just say, conduct a study, or conduct a, we have to be, So here is where you're going to brainstorm after you've all been indoctrinated with blocking and matched pairs and all this stuff. Hopefully by the end of today you can give some suggestions what would be an appropriate analysis technique. Okay, anything else?
Can you go over blinding?
What's that?
Blinding.
Blinding. Anybody else have a blank for blinding? Yeah. What is blinding? Those of you who did put something.
It's just like when they have no idea what's happening.
So for the amoxicillin, right, we have 200 people, 100 people get the amoxicillin, 100 people get the placebo. Blocking is you're hiding information from them, so they don't know that they're taking a placebo or not. They may not even know there is a placebo being given. They're just being told, here's your little pill, your medicine. That's blocking.
Yeah.
Okay. So what's the purpose of blocking? Why would you do that? So they're not influencing the outcome. Okay, so one benefit of blocking is to exclude what kind of variables? Confounding variables from, thank you. Cool. Scope is something we'll talk about maybe next class period. Okay, scope. In layman's terms, let me just tell you this. The scope of a study is how far can this study take you in your conclusions? Like, is this experiment with amoxicillin, our scope would be, is amoxicillin beneficial for sinus infections? Can we conclude anything else that amoxicillin is good for high blood pressure? Huh? It's not in the scope of the study, so no. So the scope is, what's the limit of the experiment? Like, what can you conclude and what can't you conclude? So it's important that when you guys are doing an experiment, that kind of the cherry on top of the cake, so to speak, is thinking about the scope of the study. Like, how far can this possibly take you? What are its limitations? That's what the scope is. Okay? All right, so this is the first slide on the top of page 4. So in an experiment, researchers are usually hope to see a difference in the responses so large that it is unlikely to happen just because of chance variation. We could use laws of probability to describe chance behavior to learn whether the treatment affects the larger than we would expect to see if chance were operating. If they are, we call them statistically significant. So an observed effect is so large that it would rarely occur by chance is called statistically significant. A statistically significant association of data from a well-designed experiment does not imply causation. Anybody want to translate that in English? Hi.
If the effect, whatever treatment you're giving to the subjects actually has a result, like it matters, then it's statistically significant.
You want to translate that?
Okay, so let's talk about the amoxicillin. We have two different populations. We have some people taking a placebo. Let's say 40% get better from the placebo. And 55% who take the medication get better. Is that statistically significant?
No, it isn't.
You'd have to test the null hypothesis first.
Okay, there is a null hypothesis. But is that enough variation for you to say, wow, that amoxicillin is worth its weight? What about if 95% of the people who took it get better? That is statistically significant, which means that that could not happen, but the probability of that happening by chance is very small, p-value being small, therefore it's statistically significant. Okay? In chapter 6, when we start doing probability, there's a question about an unfair coin. Hey, good to see you. So suppose you're gambling, okay, with a coin. Okay, you're not playing poker or anything. You're doing like this, like elementary school gambling with a quarter. So you go to school, and every day you're losing your lunch money because you play heads or tails, right? Now suppose you flip a coin 10 times in a row, and you only get one tail. Is that enough evidence for you to suspect that your buddy's coin is unfair?
No.
Okay, so 10, that would be statistically insignificant, right? Now suppose you flip a coin 20 times, you only get one tail.
Wow.
You'd be like, okay, yeah, what's going on here? So you would say that that is statistically significant. And actually, 1 out of 10 is pretty. You would probably have some type of suspicion, because the probability of that happening is 1 out of 1,024. So less than 1% chance of you only getting one tail out of 10.
But then you flip 20 straight heads.
That would be just as peculiar. Okay? So statistically significant would mean, could this happen by chance? Now, if you flip a coin 10 times and you get 2 tails, you'd go, oh, I'm just being unlucky. That's not statistically significant, but 0 tails or 1 tail, it's starting to raise question in your mind that something is statistically significant. So I try to give you a couple examples of what statistically significant means. So you guys try part C on the free response question. Blocking. 251. Would someone like to read that? Okay, Mr. St. Pierre. And those of you who want to look up at the little thing here,
A smarter design? The idea of blocking. Suppose that a mobile phone company is considering 2 different keyboard designs, A and B, for its new smartphone. The company decides to perform an experiment to compare the 2 keyboards using a group of 10 volunteers. The response variable is typing speed, measured in words per minute. How should the company deal with the fact that 4 of the volunteers already use a smartphone, whereas the remaining 6 volunteers do not? They could use a completely randomized design and hope that the random assignment distributes the smartphone users and non-smartphone users about evenly between the group using keyboard A and the group using keyboard B. Even so, there might be a lot of variability in typing speed in both groups because some members of each group are more familiar with smartphones than others. This additional variability might make it difficult to detect the difference in the effectiveness of the 2 keyboards. What should the researchers do? Just want a dramatic pause for a second. Because the company knows that experience with smartphones will affect typing speed, they can start by separating the volunteers into 2 groups, one with experienced smartphone users and one with inexperienced smartphone users. Each of these groups of similar subjects is known as a block. Within each block, the company could then randomly assign half of the subjects to use keyboard A and the other half to use keyboard B. To control other variables, each subject should be given the same passage to type on a quiet room with no distractions. This randomized block design helps account for the variation in typing speed that is due to experience with smartphones.
okay. So in a minute, you're going to be asked to do the same similar situation here. So for your free response on the AP Stat test, I remember someone asked, do you have to, if you draw a diagram, you have to accompany the diagram with explanation, but the explanation can supersede the diagram. You follow me? Remember that discussion with Max? Okay. Me, there's no way I can explain it without me drawing it down first. So this would be an example of a schematic on how you would do the experiment. Okay? Then once you have something like this, it's real easy to unpack it and talk about what you're going to do. But this is what you're going to be asked to do. We're going to watch a video on it as well. You're going to try number 77, then you're going to finish up the crappy. Yes, you will. Okay, so we got the 10 volunteers. We got the non-smartphone users, the smartphone users, and then within each block, we're having the 2 different keyboards. Okay? Seems like a small sample size to do anything, but anyway. Yeah. Insignificant? Yeah, but we're going to, I don't think a smartphone company would launch a new keyboard based upon this one, but. All right, so, you guys ready? So this would be an example of a randomized block design. Randomized block design.